We have just met the RIP, and now let's explore its properties. Recall the definition of the RIP. For every cardinality S, we assign a value delta S that describes the deviation from a perfect isometry. For S equals 1, we are dealing with submatrices AS that contain only one normalized atom from A, and thus Z is a scalar. Therefore, the norm squared of AS times Z is simply Z squared. Returning to the definition, this implies that delta of 1 is simply 0, giving a perfect isometry. Moving to the next property, the question we pose now is about the behavior of delta S as a function of S. The not so surprising property is that delta S is a monotonic non-decreasing function. So it starts at the 0 value for S equals 1 and grows from there. Why is it true? Think about it. Note that at some point delta S crosses the value of 1. What is the meaning of this? Let's zoom in on the lower bound of the two in exploring this case. Getting a delta S above 1 implies that the left-hand side becomes negative. Well, this is meaningless. Since being a lower bound on a norm of some vector, we know that the minimal possible value is 0. So let's focus on delta S being equal to 1. This implies that AS times Z is 0. And this exposes the fact that the columns of AS are linearly dependent. Thus, the crossing point of the value 1 means that the spark has been found. More exactly, if delta S is 0, it implies that S is the spark of A or bigger. So we see that the RIP is indeed a generalization of the spark, covering much more than the mere linear dependency property. We will now tie the RIP to the mutual coherence, a connection that will prove very useful later on. Here is the RIP property, written slightly differently by dividing by the squared norm of Z. This expression should remind you of the Rayleigh-Ritz definition of the extreme eigenvalues of the matrix B transpose B. Coming back to the RIP, delta S is the deviation of the eigenvalues of AS transpose times AS from 1. What can we say about these eigenvalues? AS transpose times AS is an S by S leading minor from the Gram matrix, and we do know several things about it. This is a positive definite matrix if S is small enough. It has 1s on its main diagonal, and all the off-diagonal entries are in the range minus mu to mu. Using the Gershgorin disk theorem, we can bound the smallest eigenvalue of this matrix from below by 1 minus S minus 1 times mu. And similarly, bound the largest eigenvalue by a similar expression, 1 plus S minus 1 times mu. Therefore, an immediate consequence of this is the relation that delta S is upper bounded by S minus 1 times mu. By the way, when S equals 1, this upper bound is 0, which aligns well with our earlier observation that delta 1 is 0. What about delta of 2? That means, what happens when S equals 2? In this case, AS has 2 columns, and it looks like this. Considering the extreme case in which the inner product between the 2 columns is exactly mu, we get that the Gershgorin bounds we have just posed are in fact tight. Thus, delta of 2 equals mu. What does this mean? Well, the mutual coherence was our attempt to characterize the behavior of the matrix A, and it did so by considering relationships between pairs of atoms from A. In that respect, mu is a perfect description for the case of cardinality 2. What about S bigger than 2? The RIP extends its view to any group of S atoms, and thus serves as an effective generalization of the mutual coherence. On the downside, however, we must mention the main shortcoming of RIP. For a general S, we cannot compute delta S, as it requires a sweep over all the possible supports of cardinality S, an exponential set of possibilities. So sometimes the coherence is all that we could afford to use.